Today is going to be about CLS, the Canadian light source synchrotron. In fact, it's the only synchrotron in Canada. It's going to be great. If you don't know what I'm talking about, check out yesterday's vlog where I talk about the experiment we're going to be doing and how the synchrotron works. Welcome to Shad. We are at the Canadian light source. Here at the synchrotron, it was a little hard to vlog there. I didn't want to disrupt science happening. So I'm going to try to switch between actual video and me explaining what's going on, a bit of commentary. Today's video is going to be a little bit geeky, a bit technical, talking about, the experiment itself, the physics behind it a bit. And so, if the technical stuff isn't your thing, feel free to skip this and watch tomorrow's vlog, which will be back to normal. And you know what the really cool thing about the synchrotron is that, well, first of all, it's the only synchrotron in Canada. A synchrotron basically is a particle accelerator. Think of the Large Hadron Collider. You guys probably all have heard of that word before. CERN, Large Hadron Collider. The Large Hadron Collider is a particle accelerator, more specifically a synchrotron. There are many, many synchrotrons in the world, but the cool thing about the Canadian light source synchrotron is that it's the only one in the world high school students can use because of the Students on the Beamline program. If you want to use a synchrotron, search it up. Students on the Beamline. That's how I got in, and that's how you guys can get in. That's the only way high school students can use the synchrotron. So at the synchrotron, it was really funny because, everything was so legitimate. There were all these really cool metal pipes and all that. But what we used to mount our sample, which was a bit of research and talking to experts, it was a WestJet 737 Boeing turbine engine. But the funny part is that with all this equipment, we ended up using a selfie stick as a mount to hold sample.
So here's a cultural thing, right? So I'm using isopropyl alcohol as the first cleaning material.
At the Canadian light source, Beamline. Alright, first scan. So what we're trying to do is that we have this plain sample part and we want to figure out what's the chemical composition of it. Now, we think that it's mostly nickel based because, a lot of plain parts use nickel. Yeah, we did our first scan.
Your neck, but everyone else can see what's going on here. So this is a software that we write here to control beamlines. It's called Aquaman, data acquisition and management software. On the right-hand side is some persistent information that gives you an idea of what's going on with the beamline. Unfortunately, this label is broken, but it would normally tell you whether the beam is on or off. You can turn the beam on and off, so this will be the same thing as hitting that button out there. Beamline energy is shown here, which you won't be changing, but it's indicated there. This shows you the intensity of the photons passing through that ion chamber that I pointed out. And this is, I actually point that out, but at the very front of the hutch there is a box that has a forge on it, like I pointed out yesterday. So it's a set of slits. So the slits are currently open to half a millimeter. And this is just for control.
So, by popular demand, Shia, you've been asked to dab. Yeah. No, do it.
We got a couple of cameras in there, right?
Just take a picture.
Take a picture of them on the screen.
Smile.
We got this little chart using the X-ray fluoroscopy chart that we created through the experiment.
Yeah, so blow up the region around. Drag around. Yeah.
Found out that the sample was made out of largely nickel, cobalt, maybe tungsten, we're not too sure, and a bit of chromium. And with each scan, we're going to be doing multiple scans. We're going to be seeing how there are different elements on different parts of the turbine depending on how we rotate it, as the color is different on each side. Like some parts are white, some parts are brown, there's a gradient. How we use the X-ray fluoroscopy graph is that the graph shows the EV, which is the electron volts, the energy of the element, and so we take that number from the graph and we look at a chart, which we have this little orange book.
100 though.
We match the energy level with what element it represents. And the funny thing was that through our results, we actually have a hint, a guide that perhaps there's a bit of dysprosium. Now the weird thing is that dysprosium is actually a rare earth metal, and because it's a rare earth metal, hint the name rare,
Right.
shouldn't really be in this sample. Our instructor told us that rare earth metals are mostly found not in nature, but when you're specifically shooting electrons and using a rare earth metal as a sample. So that's a little iffy. We don't really know. Now take a look at this. The program that we used was actually designed by some of the scientists at the Beamline, and here there's a typo. They spelled the word chlorine wrong. They forgot the H.
We got into the software by
Take a video of it.
One of our staff literally typed it out of the orange book, so it wouldn't surprise me at all.
Search it up. We actually talked to the staff about this and they thought it was pretty funny. Second scan, same as the first scan, we're measuring the shiny part that didn't rust that much from our sample. Now we're going to be doing our second scan and adjusting the sample. Eddie, you ready?
Of course I am.
It's going to be great. We also added a cobalt filter.
Good value or not. So we'd like to lock up.
To cancel out high energy so we can just focus on what materials are in the low energy zone.
So there's two ways of measuring samples. One is what we're doing in fluorescence. The other way is just to measure how much light there is before and how much light there is after as you change the energy. That's what these are meant for. It's calibration standards for that.
Eddie's doing a lockup procedure. He's kicking everyone out so they don't get killed by X-rays. Come out, Eddie. Hey! How'd it feel? You shot your first synchrotron X-ray. Feels accomplished?
Yeah.
And looking at the new graph, we're now suspecting that there's probably also a bit of copper and maybe even titanium. Third scan. We're going to be moving on to that white rusty part, moving away from the shiny grayish part. Actually kind of funny because I was putting on the gloves and they were really tight. I think I got a size too small. And on top of that, in the hatch where the beamline was, it was around like 30 degrees, so it was pretty toasty in there. And from that scan, we figured out that there perhaps was a bit of hafnium in it. Hafnium oxide when it rusts, so maybe HFO2. We actually Googled that. It's possible. You know, just Wikipedia, going through Wikipedia, searching up superalloy, you can find some connections there. And then there's this is kind of what our thing looks like. The more interesting thing is that planes use superalloys because they're strong, they're dense. Because the rust could be hafnium, that means a portion of the actual plane part probably is made out of hafnium because hafnium seeps out and reacts with oxygen to create hafnium oxide as the rust on the outside of the turbine. We also have more proof that there is hafnium where companies actually add a bit of hafnium to a plane part on the outside as a way to enhance the material overall. I'll post the link in the description below. You want to check it out. Thanks to Yazi for finding that article. Fourth and fifth scan, we did a bit of adjusting of the piece, and now we're looking at the back side, which is like the brown side where there's a gradient of all the different browns. This red crosshair. We're scanning. What we found out, it was mostly nickel, as expected. Nickel is the base of many super alloys. Also a bit of iron that we found. Because the brown part was a bit of a gradient, instead of just doing a point source, we actually had a bit of a square that we recorded.
We're damaging it enough to change the chemistry so the glow starts to disappear almost straight away.
Mapped out a whole rectangle, not just a point, and we did about 6 of these graphs, and each graph shows the distribution of a certain element. For example, copper, 1 graph for copper, 1 graph for nickel, 1 graph for iron.
Just smart. What did we just do? We just did a scan of big area, or pretty big area, in steps of 1,000 microns, which is a millimeter each.
We also burned the sample, as you can see through the dots.
With X-ray.
Previously, we didn't do that because it was mostly like a solid shade of white, so we didn't really need to do that mapping thing, and it also takes a lot of time. So what we've learned is that science is rarely certain. There's a lot of likely, there's a lot of very likely, there's some unlikely, there's some very unlikely, and there's just very few certainty. Science is all about making predictions, doing experiments, and that doesn't prove the experiment, but that points us in a direction, understand how the world works in a better way. So the science of the synchrotron is really fun, but you know what's even more fun? Buying a t-shirt.
Yay!
Now heading off to the little gift shop place and we're buying t-shirts. Excited?
Yeah. It's not a full CLS experience without a t-shirt.
So, are you buying something?
Oh yeah, I'm gonna buy a t-shirt.
Yeah?
Might even buy a postcard to send home.
Uh-huh.
Hi Mom, if you're watching this video, I miss you, and you too Dad, and my brother.
Oh man, that was deep.